Let's explore scalability fundamentals. We'll cover vertical versus horizontal scaling, Little's law and how latency, concurrency, and throughput relate, network physics and geographic constraints, the three scaling planes of compute, data, and delivery, cache stampede and thundering herd problems, and hotspots and skew in distributed systems. Let's get started. So your system needs more capacity, and you've got two ways to handle it. You can either upgrade to bigger machines, or just add more machines to the pool. Vertical scaling is basically just getting beefier hardware. You go from 8 cores to 32, from 32 gigs of RAM to 128, and boom, your database jumps from 5,000 queries per second to 15,000 without changing a single line of code. But here's the problem. The biggest commercial servers max out around 448 cores and 24 terabytes of RAM, and you've created a single point of failure where one hardware fault takes down your entire service. Horizontal scaling spreads the load across many smaller machines. Instead of one 32-core server, you run 10 4-core servers behind a load balancer. And when you need more capacity, you just add another server to the pool. So vertical is dead simple with no code changes, but hits hard limits, while horizontal gives you unlimited growth and high availability, but forces you to solve distribution problems like session management and data partitioning. So Little's law is this simple equation that explains everything about system performance. Concurrency equals throughput times latency. And when you understand this, you'll see why systems collapse under load. Here's your API handling 10,000 requests per second with 50 millisecond latency, which means you've got 500 concurrent requests in flight at any moment. Your thread pool and connection pool need to handle all 500 simultaneously. Now things go wrong, and latency jumps to 200 milliseconds. Suddenly, you need 2,000 concurrent slots to maintain the same throughput. That's 4 times more resources. And if your thread pool maxes out at 1,000 threads, requests start queuing up, and the whole system enters a death spiral. Here's where microservices make it worse. If you've got 5 services chained together and each has a P99 latency of 200 milliseconds, your end-to-end P99 approaches a full second because tail latencies compound, and one slow dependency poisons the entire request path. So you need to provision 20 to 40% headroom above your peak traffic. If you're seeing 8,000 requests per second at peak, size your infrastructure for 10 to 12,000 so you can absorb traffic spikes and survive losing an availability zone during failover. Here's the fundamental constraint. When your app in California needs data from a database in Virginia, that request has to physically travel 3,000 miles through fiber optic cables, and there's just no way around that delay. Same region communication happens in maybe 5 milliseconds, but once you go cross-country, that jumps to 80 milliseconds or more. And this isn't a bug you can fix, it's just physics. Now imagine your checkout process has to query inventory in Europe, validate payment in Asia, and update a ledger in America. Every single one of those hops adds geographic delay, and your user's just sitting there waiting for all of it to complete. The smart fix is to partition your data by location. European users write to European databases. US users write to US databases. And now almost everything stays local and fast. Here's the trade-off you can't escape. You can have fast responses by accepting potentially stale data from local caches, or you can guarantee fresh data by querying across regions and accepting slower responses, but geography makes having both impossible. Horizontal scaling isn't just one problem. It's actually 3 independent planes that all scale differently with their own bottlenecks and patterns. The compute plane is all about stateless servers. Session data and user state live in external stores like Redis, so you can spin up or kill servers in seconds without any coordination. Reddit's a great example. They launch new instances during traffic spikes, and those servers immediately start handling requests with no warm-up period or data migration needed. The data plane scales differently. Replication helps with reads, where one primary with 4 replicas can handle 5 times the read traffic. But all writes still bottleneck on that single primary. For write scaling, you need sharding. You split data across multiple shards where each has its own primary. So now writes scale linearly as you add more shards to the system. The delivery plane pushes content closer to users with CDNs caching static assets at edge locations. Reddit hits over 90% cache hit ratios, which keeps origin traffic and bandwidth costs totally manageable during viral spikes. So that's the 3 scaling planes. Compute scales with stateless elastic servers, data scales with replication and sharding, and delivery scales by caching at the edge closer to your users. So you've got 10,000 requests per second hitting your cache with a 60-second TTL, and it's serving 600,000 requests before the cache key expires. Everything's running smooth. But then, the TTL expires at exactly 12 noon, and all 10,000 requests in that 1 second see a cache miss simultaneously. They all slam the database at once, going from 500 queries per second to 10,000 in an instant. Your first instinct might be to make the TTL longer, but that just delays the problem and makes your data more stale. A 10-minute TTL means 6 million requests hit at once every 10 minutes. And adding randomness helps, but doesn't eliminate the risk, since you still get 500 misses per second for 20 seconds straight. The real solution is request coalescing. When the first request sees a cache miss, it grabs a distributed lock and starts fetching from the database, while the next 9,999 requests see that lock and just wait for the first one to finish. So instead of 10,000 database queries, you get exactly 1. You implement this with Redis using set with the NX flag for not exists and EX for expiration. The first request that successfully sets the lock wins and refreshes the cache, while everyone else either waits with a timeout or serves slightly stale data if it's still available. An even better approach is stale while revalidate. When the cache expires, you immediately return the old stale value to keep response times at 5 milliseconds, and then kick off a background job to fetch fresh data asynchronously so the next request gets the updated version. Which means your users never see slow responses and your database never gets slammed. So that's cache stampede prevention. Use request coalescing to turn 10,000 simultaneous queries into just one. Combine it with stale while revalidate to keep latency consistent, and your database stays protected, no matter how much traffic you're handling. So you've got your user database carefully sharded across 10 servers using hash of user ID, and everything should handle 10% of traffic each. But then a celebrity with 50 million followers tweets, and suddenly 80% of your reads are hammering whichever shard stores that celebrity's account. This is a hotspot, and it breaks the whole point of sharding, that one shard's latency spikes from 10 milliseconds to 500, while the other 9 shards sit mostly idle, and now your entire application waits for the slowest shard. Hash partitioning distributes keys evenly. If you've got 100 million users across 10 shards, each shard stores about 10 million users. But access patterns aren't uniform, and some users generate 1,000 times more traffic than others. Here's how you fix it. Detect when a user account or item is receiving abnormal traffic, like more than 1,000 queries per second, and cache that specific entity in Redis with a short TTL so the cache absorbs the spike while the shard handles normal traffic. Another approach is key salting. Instead of storing user 12345 on one shard, you store replica 0, replica 1, and replica 2 on 3 different shards, and reads randomly pick a replica to spread the load. Thanks for watching! If you found this helpful, hit that subscribe button and turn on notifications for more system design fundamentals. See you in the next one!